All right. Any questions before we get rolling? Besides, can we go over everything again since we had spring break and everything's been now forgotten? Did want to talk about some things I noticed with graphs labs. People are getting stuck on CN stuff. Talk about CN really quickly. So just do a loop here. That is going to keep populating. Our strings and well. Loop, two ways to do this. Of course, I have two CNs in the same statement. I also do this separately. The user doesn't have to type twice. And spit them back out. And some people were doing all kinds of get line and various other things, which don't need to do. All right, the idea is, A, B, and spits out pair of vertices. Of course, looks like I could use a new line here. I do like to forget my new lines. Right, A is a pair of vertices, or A, B is a pair of vertices. Same difference. A new line and tab, white space, all the same. To CN doesn't much care. What kind of white space it is? Yeah. And that's that's just a C++ thing. All right, different languages, different ways of dealing with strings. Yeah, strings. Excuse me. 1 second. All right, string and string manipulation is definitely something you want to study up on in whatever your primary programming language is going to be, because it's very, very commonly done operation that you're going to have to work on. It might be a comma separated values. It could be a JSON format or XML format. Usually there are libraries to help when there's a format on the data. I was going to say data structure, but I didn't want to confuse data structure versus the structure of the data, which are very similar ideas, but very different application. Anyways, that was that. Anyone have any questions about any of the labs that we had done the last couple of weeks? Anything we need to work on? Take a look at. All right. Carry on then. Where are we? So we got the practice test. Today, we'll go over that later tonight. See people have questions on that one. Anyways, we'll jump on in. Let's see, where are we? I think. Let me double check. Let's see. All right.
I actually ask a question about one of the labs.
Sure.
For the graph matrix lab, where we're using an array for like to make a graph,
Mhm.
is there like an easy way to make a 2D dynamic array?
In C++, not so much. Right. What we were doing there was a star star. All right. So yeah, so there, it can be certainly done. Easy is a different. All right, let's look at the size from the user. Then we'll go ahead and really this is a jagged array. It's just an array of arrays. And then what we do to make it rectangular, just loop for however big the size was. And then new up each of those arrays. All right, then we can do a nested loop, more or less dump it out on the screen. So we'll go for how many rows? Variables name. And then for however many columns we have. And we can start spitting out what they are. Just give me, oops. Spit out individual element. Right, so we do our, oops, forgot my matrix. Right, so we do our first indexing, to the particular row that we're going down and column. Iterate down the columns and then add some space. And then we'll spit that out and then we'll add a new line. Down with that. So it doesn't line up on the same screen. So my code's working fine. Right, we got our 5x5 matrix. And really it's jagged arrays. It's just each of these 5 arrays happen to be the same length as the number of arrays that there are.
Awesome, thank you.
If we want to make a matrix with different, yeah, so we could do, if it's not a square matrix, or if we're just doing a regular matrix, then we need different variables. Yeah. So got other stuff there. All right, it rows, calls. Asking for how many rows and how many columns. Load those up. And then still a star star. int array, and then just however many columns there are, or let's see, know how many rows there are, and each of those would have that many columns. Same here. So instead of size, it'd be columns. And then in particular was new int array based on the calls. Looping would be similar. See if I got my variables lined up correctly here or not. We'll see in a second. Rows, calls, and let's see what we did. Two for that one, 3 rows, 5 columns, or 6 columns. Looks like I got a small bug there. Missing one of the rows. Let's see. Three by 6, got the 6 part right. It's not getting that 3 right there. 0, rowless and rows. Rows, What am I doing here? Oh. All right, who sees my bug? Because I am not seeing it. Let's get some extra output here. Make sure I'm in the place that I think I'm in. How many rows? 3 and 6. Interesting. And now it's even smaller. Okay. Ah, thank you. There it is. Wrong side there, rows. And there we go. That definitely looks like the problem. 3, 6. Wait. It shouldn't be the buffer. It's interesting how did I use the same variable name over again or something? I don't know. Let me go ahead and strip out some of this extra stuff that I think my other code is missing with this code. Yeah. Ah, there's my problem. I wasn't spinning out the right array. That's again. Some big old lag here because I typed it. It's not picking. Okay, I broke the compiler. Yes, that's what we're doing. We're refreshing the page. All right, let's try that one more time. 3, 6, there we go. It helps if I print out the correct matrix. Printing out a bunch of nulls, I think is what ended up happened to be the case. And the reason why I was getting any zeros at all was printing out the old matrix. Just a bunch of white space that we couldn't see anything. Or empty space, null space. All right. Yeah, so there's your, it's still a jagged array because these individual arrays could be of varying lengths, but we built it in such that it is growing in a rectangular fashion. Number 5 through 8 for program 3. Sure. Let's go check that out. All right, height. Remember height. Let's go. Let's see. All right, this is C# just because I'm going to be doing C# much faster than I am going to be doing C++. Where's why I'm using this. All right, so height. Would be just looking at how long the legs are. Based off of left sides and right sides. So if there are sides, all right, no, there's two ways to do base case checking. One way of doing it is once you're in here, right, if the root's null, then right, return back our base case. And there's also pre-checking, right? So we could do before checking, we could also say if root left not equal null, then we can go ahead and get the height on the left side. Equals, get the height of root left. Interesting how it jumps to the equals. Anyways, and same idea with the right. Right, we could do if root to right equal null. Right, equals height on left hand side, or rather the right hand side. Got stuck staring at the little squiggly over there. Right, so we're being a little bit redundant by doing both ways. Let's see what is. Let's do the max here. Well, let's do it if right, grid left, right, always left, and adding 1 for itself. Initialize, always important to do. Okay, so right. I'm being a little bit redundant here because I'm in control of the code here. And I'm not really handling an empty root saying, yeah, your tree is empty, but whatever. So if I were to run it right now, and just spit out the height of the tree, right? Should say -1 at this point. Let's have a bug, right? Because it's an empty tree. Doesn't say the tree's empty, whatever. Different ways we can do that. Right now, I need both ways of this because, and I don't need both ways. But if I get rid of this check, right, somewhere we need the base case for us to return -1s. The typical way of recursion is to have the recursion base case in there directly, and we just go ahead and pop back out and not have to do all this fun stuff because it's wouldn't change anything. So if I comment out and actually had a tree, it should be the same thing. Don't actually have a tree just yet, so just say -1. And of course, always good to actually have something. Yeah, we'll do bool. All right, and lots of different ways to add. Since adding is only going down a single branch, there's not much benefit to it being recursive. And then return true, saying we added it. Right. Otherwise, we just do our left to right behavior. At this point, we're just testing, deciding which way to go. All right, if the data is less than, and node. Be careful here, so I'll break my tree. The loop. I'm just going to keep on looping until we find who we're looking for. So it's less than the parent data. We'll go left. Right, our left logic is going to be if parent left is an empty branch. Then we can go and attach it, and then we'll be done. And then we got a constructor here because it's getting to be a bit annoying to have to say data equals data all over the place. And of course, the other way we could do it is just create the new node in one place and just set it up. At that point, right, because seeing new node data over and over in the code here, it's a little bit redundant. So that's one of the things we can do to reduce things, is just go ahead and create a new node and just find out where it gets attached down later. All right, and if it's not null, we'll just go ahead and slide to the left. All right, good enough for now. So we'll just add one root value and a smaller value. Spit things out. Add 10. Spit the height out, make sure things are growing correctly. And then we can add something smaller. And print things out and make sure things are growing correctly. Or if we have bugs. All right, what do we got there? I'm trying to write C++. All right, so the tree was empty. The tree had one node. The tree had two nodes. Of course, you can't do any other test cases at the moment because we only have half the battle for building the tree, but that's the general idea. For getting the height, let's see, if that was number 5, 6 leaves. It's still all the same idea. You're just looking at the tree a little bit differently. So a leaf, you're just going to be testing if we have a node that is a leaf, right? And the node is a leaf. If its children are both null. So our base case, if the root's null, just turn 0. There's nothing to add to the data set. Otherwise, we need to find how many leaves are on the left-hand side, however many leaves there are on the right-hand side, and test to see if we are a leaf. So if we are a leaf, means left is non-existent and right is non-existent. Then we are a leaf. And then otherwise we'll return the sum of however many leaves there are on either side. All right, so we can add leaves into our, let's see. Which is just going to be 1 each time the way that this tree is. Or it should be 0 when it's empty. All right, 0 leaves, then we go 1 leaf and then 1 leaf. All right, it's the same idea, just recurring on ourselves, working down left and or right sides. And just different analysis of what we're doing with the data. 7, search for name. Search for name is the same as inserting, except for looking for the data instead of building onto the tree. And 8 is just going to be a traversal, right? Just do a pure traversal, basically. Now, private, need the outside world knowing about inner workings. Publicant. Lightest. And let's take, let's see here. It's going to have a seed value. So if the root's null, just spit out an error. Tree is empty. And return -1. Otherwise, the lightest. We'll start the ball off with the current lightest, which is the root. So the root's the lightest person until we find out differently. So what we're going to do is get the left lightest by calling lightest again. Root left. And whatever our current lightest is. And we need our logic and all that fun stuff. It's the same idea for the right. All right, so if roots null, we'll just return back whatever was passed in as the lightest. Otherwise, if left is less than lightest, lightest goes left. If right is less than the lightest, then lightest. It feels like I'm spelling that wrong. Lightest equals right sort of thing. And we return back the lightest data at that point. This one's just using it. I'm using names and numbers. So it's not fully same idea. Because we'll be looking at the different data point, but same general idea. Empty tree. So we're saying the lightest is -1, then the lightest is 10. And it seems I have a bug here because it didn't switch over to 5. Let's see. If right. Just last. I need to step through there. Of course, the other wrinkle here I forgot to code for was that -1 scenario. But by doing lattice, I was trying to avoid that situation. Let's see. Oh, I'm not looking at that. Sorry. Need to be. I'm not looking at the node data as I'm going through here. So there's my bug. So I just need to tweak that to actually look at the node data when we get in there. That's what I kind of forgot to do. But yeah, I'm never looking at this node's data anymore. I just kept passing around the same value. So I keep comparing 10 over and over again. With that, that's in the right direction. You have to tweak that. Okay, so for yes, if you wanted a 3-dimensional matrix, yeah, that would just be triple stars. And definitely don't want to go playing in that one. It's the same idea. If you create the number of planes, so we create a planes variable. You want 5 planes of 2x4 matrices. Same idea, right? It's a pointer to a pointer to a pointer to actually get down to. So it's just arrays. The outer array is just the individual planes, and then once you then navigate into that one, then you get to the rows within that particular plane, and then down into that column for that particular row for that particular plane. Yeah, you can have as many stars as you need to represent the number of dimensions that you need, but it's very uncommon to see more than 2 dimensions. Most of the time, when you deal with arrays, they are 1-dimensional. Occasionally, you get to 2. All right. Any other questions? Let's see. Where's that? Okay, so we're talking about Euler graphs. Let's see. Graphs. So any questions about the graph matrices or lists? Right. At this point, can I understand how that's working? Double check. All right, let's go here, 4.4. The link. Drop the link in the chat, and then Dijkstra single point, shortest path. Link for that. What I'm doing here is for weighted graphs with non-negative. Oops. Okay. That's our objective here. All right, so what we're trying to do is find shortest path from a single starting vertex to all other vertices in the graph. There is a precondition that all the weighted edges are non-negative. Otherwise, the greedy algorithm is not going to work. All right. So I don't remember talking about grid algorithms or not, but I'll mention it again. Grid algorithm is when faced with a decision. Faced with a decision. Choice that is made is taking what is of the greatest value to the objective. All right, so our objective is shortest paths. So when we're choosing paths, we want to choose the path that is the shortest amongst paths. All right, so the way the algorithm works is we'll start to build paths from the source vertex away from that vertex, where when we decide which path we want to build, that will be the shortest path. So let's go over what I'm talking about. All right, we'll need a fair number of vertices in here so that we can get some paths to build. All right. Just arbitrary letters, A, B, C, D, etc. And we will need a bunch of weights in this graph. That will provide us with various options for where we can go to. Okay. All right. Bunch of weights. Our objective being finding shorter paths. So we'll just arbitrarily start with A as our starting point. And we'll build up as we go along from there. Different ways that we're going to be able to go. All right, so for the above graph, using A as source vertex, figure out paths from there. So we're going to be using a table to track this. We have our source vertex, destination vertex, distance to get to that destination, and if it's known to be the shortest path or not yet. All right, so just toss in our various vertices and alphabetical, because alphabetical is generally preferred. So our initial state, and I got this backwards, sorry. Get my source and destination backwards. So our initial state, everything is false. We don't know how to get to B just yet. A and how much it costs to get there. So what we're going to do is from the current vertex, we're processing. look at its neighbors and see what path or potential path information we can use to populate the table. All right, so I'll do a lot of copy pasting of this table here so we can come back and see everything that happened after the fact. All right, can you do a split? Probably not. Maybe we should grab the image. So we can look and see at the same time. Now this algorithm, of course, is not using an image to do its job. It would be using the underlying adjacency matrix or list, whichever we chose to use to process the data. Right, so if we're using an adjacency matrix and we're using A, that means we're looking at the row A in the matrix. And then we're looking to see, is B a neighbor? Yes, it is. And it costs 3 to get from A to B. So what we'll do is we'll go ahead and come to the table, say we can build a path to B. We get there from A, and it would cost us 3 to get there. We don't know that's the best path to get there just yet, so we can't mark that as known. Right, so we've looked at this edge, and then we'll look at AD next, because that's where we would be in matrix. And we come along and do the same thing here. So we can get to D from A, and it would cost us 1 to get there. That edge is processed. And go ahead and process this edge, A to E. And it would cost us 8 to get there. All right, so now that we've consumed neighbor data from A, the A node, next we'll be greedy and choose to build a path to a node that we don't already have a known shortest path. All right, so we have 3 options. You can build the road to B, for a cost of 3. And we have D for a cost of 1, and lastly, E for a cost of 8. Since we're trying to minimize the total path distance, we'll take the shortest path. So we'll choose build the path. And I just realized I didn't make the data the way I meant to be. That's fine. We'll get there. To the D vertex, marking known value for the D record to true. All right, so we'll just do one thing here. We will set D to true. We know that this is going to be the shortest path to get from A to D. There's no other possible path to take. And if there were going to be a shorter path, we would have built that way otherwise. All right. The node we just built the path to. It's now the node that will process neighbor data from. So we'll do as we did before. Using B node, get neighbors. All right, so from B has an option to go to C. Don't have any information here, so we'll just go ahead and dump in the data. Now the distance is going to be the sum of the full path length. So it costs 4 to get from B to C, Plus it took us 3 to get to B. And hell, here, look at, I'm goofing up here. 1 second. We're using the D node. Let's process the right information. Okay, back to what we're doing. All right, looking at the neighbors. This edge, the AD edge has already been processed. There's no new information there. We do have this edge, DE. And we have information already in the E record. All right, so the E record is not known to be the shortest path, so we might be replacing it. The present information we have is we can get to E from A for a total cost of 8. Alternatively, we can go from A to D, and then from D to E for a total cost of 1 plus 2, and that's going to be an improvement over our existing information. This mistake there. So instead of going to E directly from A, we will instead first go to D and then go to E. Right, so basically saying A to E direct route, 5 freeway, 8 o'clock in the morning. Yeah, good luck with the traffic. Side streets are going to be the better bet for where we happen to be, sort of thing. Right, so the direct hop isn't necessarily going to be the best hop. There aren't any other edges to process there, so that's all we're going to update. And we'll do the same thing again. Choose E. Oops. Hold on, I'm getting ahead of myself. All right, so now we must choose. We have 2 paths that we can build from. Right, the D path is completed. The A path is start off completed. We have no information on paths for C, F, and G just yet. So we must choose between going to B for 3 versus going to D for 3. Choose the path to build, either 3 to B or 3 to E. All right, so when finding minimum in a set of data, the first smallest is the smallest until we find something smaller. Right, so B is the first smallest node that we found based on the distances. So that is the path that we're going to use. Just go ahead and update this 1 plus 2 to a 3. Keep the table simpler. All right, BC. C has no information, so we can get there from B for a total cost of 3 plus 4. 3 to get from A to B, and then 4 to get from B to C. And then we have BE. E says we can get there for 6. Alternatively, we can get there for 3 plus 3. 3 plus 3 is not an improvement over 6. We will leave this record alone. This edge is not used, and this edge, as we had before, was discarded. So we have 2 roads. If we look at the full build at the moment, let's see. Let's go. And so the path, that path is known shortest. That path is known shortest. This path is known shortest. AB is known, AD is known. So the blue part is the for sure paths. The red parts are potential growth. All right, so we've processed B, we marked it as true, and we can carry on. Let's see, I think I remember to bold D when marked as a state change. Okay, so B got set and we updated. Let's see here. All right, and then as before, choose from potential paths. We have to C for 7 and to E for 3. All right, so we choose E. Choosing E, we'll flag that as true. And then using E, process whatever edges it may have. We just have the one. So go ahead and build that out. Actually, before I get there, let's build the path, mark it blue. And process this edge. Since we don't have any edge data to F, go ahead and drop in E here as our source. And what are we going to put for our total distance? Just toss a number in the chat if your keyboard's working. If A is our starting vertex, what is it going to cost us to get to F? 8's 3 plus 5, all good answers, right? 3 plus 5 took us 3 to get to E, which is a 1 plus 2, but that doesn't much matter at the moment. 1 plus 2 plus 5, right? Also full cost, but just from the current state of the table, we can use the 3, oops, that's in the table, and then add to it from the matrix or the list, the 5 that it's showing there as F as a neighbor. Right, so that edge is processed. We didn't eliminate any data. There are no additional edges from E to process. We can go ahead and continue on. So E got bolded and F got added. All right, so we have, let's do some collapsing our data points. All right, 8 and 7 to choose from. So we'll go ahead and choose C. Choosing C, we flag that as true. Choosing C means we can mark that path as known. Get to C from B, as the table says, get to C from B. And now we can go ahead and process any edges that it has, right? So we have CF, CG, CF says I can get to F for an additional 2, right? So we have 7 plus 9 versus our 8. 8 is going to stay there. So go ahead and eliminate that. And we have C to G for an additional 8. And it costs us 78 here. So that's a big fat 15. And I just noticed I'm missing a weight for this edge. So we'll add an edge there. We should go ahead and do 4. I'll add that to an image above in a minute. And that's where we are after choosing C. 2 vertices that we don't know how to get to yet, and 2 potential paths that we're building. Right, chose C, so we set that to true, and we added G in here. 7 plus 5, 7 plus 8 rather. It was just 15. Okay. All right, easy decision. 8 versus 15. Choose F, which marks that as true. And then F says we can get to G for 4, which will be an improvement. 8 plus 4 is much better than what we had before. Which means we can go ahead and toss that edge from consideration when we erased it from the table. And then the last thing to do is just go ahead and mark the last data point as known. And then set. Last node. As true. Right, so this is the final state of the table. All the paths are known. We know how much it costs to get to G. It costs us 12. How much it costs to get to C? It costs us 7. We know the cost to get to anywhere, and we know how to get there. So if I want to know how to get to G, look at the source vertex, go back to that entry, F, source vertex E, E is D, D is A. All right, so that's the full path to get there. So by working backwards, can see the actual path, the vertex, in addition to the cost to get there, just looking at the table. And mark this blue. Grab our final chart and get back up here and add that 4 in. All right, so the advantage of this algorithm is it does not evaluate every potential path that we could possibly make, right? Because there's the path to get to D, we could have gone A, B, E, D, we could have gone A, B, C, F, E, D, right? But we're a lot of those other potential paths that we're completely discarding and even considering are going out of their way. So the idea is we just keep building the road that is the shortest hop away and just build up from there. Now, this particular question can be a little bit time consuming on the test. So what I would do, in fact, let's go ahead and I'll do that. I'll just put it on the maybe to run to the practice test for the graphs test. All right, so I will just toss some graphs out there and you guys can work on what the shortest path is. But each time we process a node, that's an iteration that we're going through. And on the test, I'll be like, I've already built it up to like B, and you do 2 more iterations. So we build up whatever the next 2 vertices are, sort of thing. We'll see that when we get around the practice test. But yeah, it's certainly a fair amount of time going into here for all the work, right? We're basically processing all the edges. And then depending on how connected things are, right? V log V. Remember if I mentioned O notations before yet or not in our graph sections, but this is we're changing from a single variable to a multivariable O notation or asymptotic notation. In our case, we've got our theta. Right? N no longer applies. There is no N in the context of graphs because graphs is not a single data point. It's 2 data points. It's how many vertices are there and then how many edges are there, because you can have a 20 vertex graph that has 19 edges, or you could have a 20 vertex graph that's got what's the summation of 20? You know, about 200 edges. Right, so the weight cost of the edges could be a heavier factor than the cost of just the vertices. Right, and in the case of a complete graph, it certainly would be, because a complete graph is going to be quadratic in terms of number of edges it has, versus here we have a v log v. Right, so 20 log v is going to be a much smaller number than 20 squared. Dijkstra, yeah, 1959. This algorithm's older than probably everyone here in this meeting. Been around for a good fair amount of time. GIFs are always good. Right, and very often the algorithm is used to figure out once we get there, as this GIF is showing, right? So it's not guessing from one place to all places. Building routing tables, I believe, is based on Dijkstra's algorithm. So when we get packets in, we need to get from where the router is. The router is the single starting point, and then all the other places that it can get to that router knows about it are the destinations, and we want to be able to figure out, where do I need to forward things on, right? So a routing table would want to basically be tracking that data with something similar to the table we were looking at here, right? Packet. We're at vertex A in that particular bit of the internet, and we're trying to route this packet to wherever the IP says that packet's going to, and to get the next hop type thing. Let's see. So that's Dijkstra's algorithm. There's another similar algorithm in this area. All pair shortest. All pairs. Shortest path. Floyd Warshall. Hey. Let's find Floyd Warshall. Oops. All right, so this algorithm will find the cost to get from any vertex to any other vertex. Okay, so the algorithm, is going to use each vertex in the graph as a jumping point to go from a pair of other vertices, iterating through in a just a big O V cubed pattern. That's the wrong way. All right, I already forgot my superscript. Super, the period. I thought. Okay. Here, other vertices. All right, so this one being cubic, definitely. And we'll steal this one. It's a long running. Long running algorithm. So much so that I am going to murder a bunch of the vertices in here. All right. We use this data to work from, right? So the shortest path from A to B, the shortest path from A to D, the shortest path from A to E, the shortest path in the reverse, B to A, B to E, et cetera, B to D, right? It doesn't have a direct context, so we have to figure that out. Go grab the pseudocode to show you on the screen here. Too big. All right, so this one's going to be heavily relying on the matrix. So we're going to go ahead and get that in there. And get A, B, C, and D. Let's make this a little bit smaller so we can get more on the screen. All right, A, B, C, and D. All right, so again, A has 2 edges. Got B for 3, D for 1, which means we have no data or infinity for A getting to itself. A, B, D, thank you. All right, B gets the A and E for 3 apiece. No data for the 2 other vertices. D gets the A for 1, E for 2. Data and E. Oh, I forgot my edge there. Totally. All right, I gotta fix things up here. That's gotta be fixed. All right, 8. All right. 318, 318. Nothing on the diagonal. So E, A for 8, B for 3, and D for 2. Okay. So what we'll do is we're going to be doing a bunch of comparing. Right, so it's saying from K, I, and J. Right, so there's our cost. Number of vertices, number of vertices, number of vertices. There's our good old cubic. And we're just going to compare a position, right, 1, 1 versus the sum of, then the first time 1, 1 plus 1, 1. And if the sum, if that element is greater than the sum, we'll replace that particular element with that sum. Right, so what we're doing is we're using A as our reference vertex to see what we want to do. So these values and these values we're going to use to look at all the other elements. The algorithm is going to look at itself, but yourself plus another non-negative number is not going to be less than yourself. So it doesn't much matter to look at these. So the first data point we'll look at is B to B. So it goes through an iteration, and then we get down, right? So we went down our first row. Now we got I incremented to 2, so now we're looking at B, and we're going to be comparing this particular element's value, which is not known or infinity, versus the sum of 1, 2, and 2, 1, right? Which is, A, B, B, A. So we're seeing, right? So B to B. Going back to the graph, we can go from, get my notations here, right? B is trying to use A as a jumping point. So we can jump to A, and since we're looking at the B to B cell, we're looking to see what's the cost to jump back. So B can go to A for 3, and then back for an additional 3. So that means we can go ahead and replace that with 6, those 2 numbers. Now B to D. Go ahead and clear all that. Still the same jumping vertex. B can go to A for 3, and then from A to D for an additional 1, 3 plus 1. Right, so B to A, and then from A to D for 1. So we'll replace that with an improvement there. Right now, B can get to E for 3. But instead of going directly there, we could alternatively go this way. That way is a cost of 11. So since that's not an improvement, we're going to leave that 3 data point alone. So this data point stays as it is. And then we will keep on doing the same thing, which is iterating down. Compare this value versus the bolded values. Since 1 plus 3 is an improvement. All right, D can go to A for 1, and now that we're at A can go to B for 3. Right, the mirror of what we had over here. 1 plus 1, better than no shortest distance, right? If A is where you are and B, D, and E are the restaurants you're choosing from or the grocery stores you're choosing from, and your discerning factor is whoever's closest is the one you're going to. You want to know what's the closest loop back, because I'm only going to the grocery store and back, gas station and back, whatever it is. Right, if you start doing multiple things, going to the grocery store and the gas station, well, now we've got, okay, closest path from me to the grocery store and from that grocery store to the gas stations, right? Lots of data points to process. All right, so 2 versus 1 plus 8, no improvement. 3 versus 8 and 3, 2 versus 8 and 1. And then we got to go the old 16 here. And that is one iteration. Okay. That's for K equals 1. Now K goes to 2. So we'll use B as the jump vertex. Go ahead and replace our numbers here. Yeah, this one should have been 3 plus 3. Consistent. So we'll look at the bolded values versus every other element. And if it's better, we replace. Right, 1 versus 7, no replacement. 8 versus 6, so we'll replace. Right, we're saying B. Instead of going from A to E for 8, A to B for 3, B to E for 3, 6 is better than 8, and so on and so forth. Skip the B row because that's where we are. 1 versus 7, 2 versus 8, 2 versus 7. And then we have our mirror, 3 plus 3. 2 versus 7, and then 3 plus 3. And the party keeps on continuing. Our outer loop now goes to 3, as it were, using D. Jump vertex. And we'll replace these with their collapsed versions. All right, so this one, 1 plus 1 versus 6 will replace 3 versus 5, 6 versus 3. And continue on, not an improvement, not an improvement, not an improvement. And we've got our mirror case. Not an improvement, and then we improve again over here. How are we doing so far? What are we going to use as our next jump vertex? What shall we replace this part here with? He's good. All right, our last vertex to process. We need to toggle our bolding. That. Let's try that again. Yeah, I can do optimization. Toggle. Okay. And look at you, bold that guy. All right. Simplify the data. And see what E may bring us. All right, so quickly look, we instead of adding everything up, we see this E is 3, so look for anything that's less than 3. There's nothing, or rather greater than 3. 3, anything greater than 3, yep. 6 is greater, so we're going to do that. 3 plus 3 is the same. 3 plus 2, non-improvement. Greater 4 is not lower than 5, and we're done. All right, so shortest path from A to anyone else. It's going to be 2, 3, 1, and 3. We don't know what the actual path is, but we know what the cost is going to be. And sometimes, typically this is a information that other algorithms will use so they can more or less constrain themselves. So they like trying to build a shortest path. We know shortest path to get from D to B is 4, and I'm building a path. I'm already at 4, but I'm not there yet. Then I can abandon that path. And we know that path is not going to bear fruit because I'm already at matching value. I'm just trying to figure out what the path is at this point based off of the current state of the machine. That's the idea of Floyd Warshall there. All right, check out Wikipedia. All right, negative things, of course, tends to mess things up. Otherwise, that's pretty much all there is to Floyd and Warshall. Questions at the moment? All right, let's go ahead and take a 5-minute break. And we roll back and continue on. All right. Next up is a spanning tree. A spanning tree is a subgraph on a connected graph where that tree includes all the vertices in that graph. Just remember, a tree is an acyclic graph, and there's lots of ways, right? More cycles there are in a graph, more spanning trees that can be built from that graph. So if we start with a simple 4-vertex cycle graph, several ways that we can turn this into a spanning tree. All right, so basically just remove one of the vertices. Excuse me, one of the edges from the graph. And we have a spanning tree. Just doing a different edge each time in no particular order. Right, so for this particular graph, we have 4 possible spanning trees. All right, so any cycle graph will have as many possible spanning trees as there are edges. All right, so as we get to general graphs that don't have a particular shape, trying to get spanning trees from that, all potential spanning trees can be quite arduous, but typically we care more about a minimum spanning tree. All right, so the minimum spanning tree is the tree in a weighted graph with the smallest total cost path length. All right, so if we take those as we did before and add some data, all right, 1, 3, 4, and just say 7. When we go ahead and remove edges here, now we're going to start getting some differences between these spanning trees. All right, so we killed the 4 on that one, we killed the 7 there, killed the 1, and we killed 3. So our path lengths, this one, 7 plus 1 plus 3, giving us total path length of 11. Here we have 1 plus 3 plus 4, giving us 8. 7 plus 4 plus 3, giving us 14. And lastly, 1 plus 7 plus 4, giving us 12. All right, so this particular minimum spanning tree, or this particular spanning tree is the minimum spanning tree because 8 is less than 11, 14, and 12. There's a small sway. We achieved getting that by removing the edge with the highest cost. All right, so we had a choice between removing 1, 3, 4, and 7. In this particular spanning tree, decided to remove the 7, and as such, that is what drove it to being the smallest spanning tree. All right, so there are several algorithms. We have two or several, two. And we do two. Yeah. 0.6a. No, my brain's not working correctly. I believe it's Hamiltonian's algorithm. Hamiltonian. All right, brains spacing minimum. Prim is the other one. Or is it Kruskal? It must be Kruskal. Where is it? Kruskal. There we are. All right, that's what I want. And there's Prim. Kruskal's, what we're going to look at here first. I pull the name back out. The recesses of my mind. All right, so objective. Find the or one of the smallest spanning tree. Step 1, sort the edges. Step 2, add an edge to the tree. If a cycle is detected, move the edge that we just added. Then we'll stop when we have v minus 1 edges added. All right. Go ahead and keep it simple. We'll use our little 4 vertex graph here to start. All right, let's try that again. All right, so our sorted edges. We have AB, BC, CD, and then AD. So we'll go ahead and do, just start adding. And since this one's quite simple, it will, what you do here on the screen? Okay. We'll draw. So adding AB. AB does not create a cycle. So the edge is added just fine, and we'll go ahead and process along. Sorted edges, same thing, just one fewer edge available to process. Then we'll go ahead and add. So take BC. BC does not create a cycle. So we're done with that. And we've got our sorted edges. Last we have is CD. And that edge, no cycle is detected. We can't get anywhere else. And we're done. Sorted edges just has AD left in it. And there's no point in adding this edge, because if we add that edge, we're just going to create a cycle and then remove the heaviest edge. And the heaviest edge is the one we just added. So there's no reason to continue processing at this point. So let's go dig back to a bigger graph. All right, so sorted edges. See, we've got AD as a 1. What are our 2s? So we got, all right, so making sure that you're sorting properly is important. So we're going to be doing a stable sort. All right, so that's, okay, let's just list out the edges. Right, so we go to the matrix and we start at A. You see it gets to B. All right, grab it. A gets to D. Grab it. A gets to E, and we grab it. All right, these are the 3 edges that exist from A. Move along to B. B gets to C. For 4, BA is an edge that's already an edge we have, so we're not listing that again. BE for 3. 2 edges are processed. Move along to C. CF for 2. CG for 8. Move along to D. DE for 2. That's it for there. E has F for 5. F has G for 4. Make sure for everybody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. All right, now sorted with a stable sort. All right, so stable sort says, we just grab. All right, so a selection sort would be stable because we just grab the smallest append. That's our only one. Let's go through, grab our 2s. Grab our 2. That's all our 2s, and we've got our 3. And 3, et cetera, et cetera. Move on to 4s. Five. And we got any 6s? No. Any 7s? No. Pair of 8s. All right, and then we just keep adding. So we'll add 80. Draw that. Draw that. 80 is added. That's in the tree. Add CF. CF's over here. You see that tree is in a disconnected state. Eventually it'll grow together, potentially making cycles as we go along. DE. DE, no cycles. We keep on carrying along. Add AB. Let's see. So I need a little bit more space here. So redraw that. 1. Let's skip someone. So we did 1, 2, there we are. Yep, there we go. Okay. Just where I was. All right. Add BE. Add BE. All right, BE creates a cycle. Since we don't like cycles, we will go ahead and kill that edge. Remove BE as removed from the tree. So we process BE, didn't like it, carry it on. We still have not hit our goal of 6 edges, right? We have 7 vertices, we need 6 edges. Presently we're at 4. So next up, BC. BC did not create any cycles. Then we try to add FG. FG does not create any cycles. And we have 1, 2, 3, 4, 5, 6 edges. So we're done. All right, these last 3 edges are not going to get processed because if we process them, that creates a cycle, and that creates a cycle, and that creates a cycle. All right, if there are multiple duplicate weights, it is possible for there to be more than one minimum spanning tree. The labeling of the vertices will drive which would be the one chosen. Good. Screen grab of that. How are we doing with Kruskal's algorithm for getting a minimum spanning tree? All right. We have another way to try to find a minimum spanning tree. Prim's algorithm. Prim's minimum spanning tree. So with Prim, we'll arbitrarily choose a vertex to make the root of the tree. And we'll grow that tree by adding vertices that are not yet in the tree to the tree. Prim is greedy and will choose the vertex that is closest to the existing tree as we're deciding whom to add next. All right, so we'll do this like we did before. We'll start small and get bigger from there, right? So every vertex is going to be in the spanning tree at the end, which is why it's pretty arbitrary. Who to add first. So we'll just go ahead and say we're going to start with D. Then bring D into, so D is our starting vertex. And then we have a choice at this point. We can, let's see, we can build out from D to A, or you can build out from D to C. So we have two choices at this point. C is closer to our tree, D, than A is. So what we'll do is we'll go ahead and choose to include C into the tree. From D. All right, so now our tree has grown. We have D and C in the tree. From here, we have two options. We can build the tree from D to A for 7, or we can build the tree to B from C for 3. And we'll go ahead and be greedy and choose the smaller of those two. As we add them in. Oops. And two choices again. D to A for 7 or B to A for 1. All right, so we'll be greedy. And we'll include the shorter edge. And A is now in the tree. All right, since there was just the one minimum spanning tree, that's the one we chose. Let me go ahead and add some colors here. Let's try that again. Let's make those red as potential edges to choose from. Potential edges and potential, nope. Potential edges. All right. And you can see the final minimum spanning tree that we got. If we go ahead and kill the edges that are not in the tree, this was more than just a color delta. Right, it's the same minimum spanning tree that we got. We're talking about minimum spanning trees, and we manually did it ourselves. All right. All right, so to track all this data, we're going to be maintaining a table much like we had with Dijkstra's algorithm for single point shortest path. So we'll do the skin with our table, tracking the data instead of the image. All right, so insert our table. Get 4 vertices, cost 3. Yeah, whether or not it's in the tree. So we've got our vertex. My brain on here, distance, including the tree. So we have A, B, C, and D. All right, so we started at D. D is included. All right, so starting at D. This is our initial state. All right. Whatever distance 0 does much apply. Process D. D says I can get to C. All right, I did get these backwards just like I did before. All right, so D's in the tree. From D, which doesn't matter too much for the algorithm, but it's just easier to track what's going on. right? TC 4, it's not in the tree. Today 7, it's not in the tree, right? Blank and false mean the same thing, but I just want to have the record be full there. And amongst the false nodes, non-nulls, choose whoever's closest. Choose closest. All right, so we added that data, and we're going to go ahead and mark that as true, as included in the tree. All right, C and D are in the tree. So now we need to process C, right, as it was just added to the tree. All right, go get my image. Toss that over here. Right, or I could just bring up the matrix and use that. But C's added in one extra edge to B for 3. So the difference here, right, with Dijkstra, we were adding values together. Here, we're not adding values, just using the values straight from the matrix or the list, because that's how it is, how far away it is to add from the tree. But it's not in the tree yet. All right. Be greedy. Go ahead and be greedy. And we'll mark the smallest one as true. So B is now in the tree. Ooh, that is the wrong key. All right, so B comes along and says, here's this edge to A. All right, so we're going to process B. B says, I have this edge to A. And the edge you presently have 7. 1 is better than 7, so we'll go ahead and replace that. And then we can be greedy. Greed. Mark it as true. And that's our final state change. And here we had our state change there. Since the particular graph has exactly one minimum spanning tree, both algorithms would take us to the same answer. Right, then we got a nice animation in here somewhere. There it is. Right, I don't know which one they started from, but they're basically looking at who's close to the tree. So when you get things are close, that was close. That one's really close. That gets that one, and then close, close, and then we're going to branch for somewhere. There we go. And these ones got some fair distances here, so we're looking for the shorter ones. And then we find our way. Close, close. So that one looks like closer. There, got me. All right. And it finds the spanning tree. All right. Spanning trees are also constructs that tend to be used as building blocks for other algorithms. Sometimes I think I mentioned some briefly like this for infrastructure, right? Sewer, water, gas, electrical, whatever. Starting point is the power plant or the waste reclamation plant or wherever the water source is, sort of thing. And we want to get all that to everywhere else. Minimum spanning tree would be the least amount of pipe to lay. That's assuming the costs are equivalent. In actual applications, it can be a little bit different because, right, coming from the main line, we're probably talking about like a 4-foot pipe of water coming out here. But as we get further and further away, there's less and less water that needs to be distributed downstream from there, so the pipes can get smaller. And it's going to be less expensive to install a 3-foot pipe, a 2-foot pipe, a 1-foot pipe, right? A 4-inch pipe, however big the pipes are, then going into your house is probably like, what is that, 1-inch pipe or whatever it is. right? Those are going to be less expensive to install. So just pure minimum spanning tree may not necessarily give you the best cost for installation and all that fun stuff. Let's see. There's our good complexities, proofs, always fun stuff. I'm trying to think what else. Some of our traveling salesman problems are going to use that minimum spanning tree. Yeah, I think Dijkstra is very similar. Grioids, I don't know what that one is. Oh, for correctness, that's perfect. All right, so when we do our traveling salesperson, minimum spanning tree will be something that we'll use to help set bounds. And then from that, some algorithms will basically use the tree as a starting point to then build it out. Let's see what time. 8 o'clock. All right. So that was for the small tree. Let's go ahead and take it up to the bigger tree. All right, so let's get a new line here. 7 vertices. Copy. Good enough. Do. Too many rows. All right, so where shall we start? Anyone have a preference for their favorite letter of the alphabet amongst this subset of the alphabet? Anything, anyone? F it is. All right, so F is our starting vertex. F is included. All right, this will give us 3 edges to process. F to C for 2, F to E for 5, and G for 4. Whom shall we add? What choice are we going to make at this point? Which vertex gets pulled into our tree? Got to vote for C. Everyone agrees by saying nothing else. 2 people say C. Now, if 2 people say it, they must be speaking for the entire class then, right? All right, so C is in. Let's go ahead and put some circles here so we know who's in, who's out. And we will grow potentially these ways. All right, so we have 2 ways getting to G. Only one's going to be kept. And we will keep the smaller of the 2, so we'll toss that new information. Getting over to B, that's wholly new. Prim C for 4. And C is included. All right, who's next? Who shall we add in? Well, we can't add A. We don't know how to get there yet. Gotta vote for B. There's B. All right, so we had 2 4s, and the first 4 wins. So we'll include B in. B is in the tree. And 2 edges, not yet processed. All right, so A is wholly new information, so we'll go ahead and put that in there. E, now we have 2 choices. Are we going to keep the 3 or are we going to keep the 5 as the potential growth path here. Keep 3 or keep 5? Who shall I stamp out? Keep the 3. Sounds like a good plan. All right. Now we have choices 3, 5, and 4. 3, 5, and 4. 3 being the smallest. A is pulled in. Now that we've pulled A in, we're going to go find its edges that we have not already seen. It gives us 1 and an 8. And that 8 is not useful information. That 1 is useful information, so we keep that. Choice between 1, 5, and 4. So we'll go ahead and take the 1. D is in. Then we've got a 2 here. So what do we do with this edge? Is it take over or are we tossing it? The DE edge. All right, E is not, in fact, I forgot to replace it earlier when I did the murdering. Presently, we have B3. Is getting to E from B for 3 better than getting to E from D for 2? Have I lulled everyone to sleep already? How's your relational operator working? Is it processing data just fine? What's smaller, 101 or 010? Let's go binary. Let's see if I can twist things around. All right. We're only going to keep one potential edge into any vertex at any given time with this table. And the one we want to keep is the smaller of them. So to get to E, we'll keep our 2 data point. Make our choice between 2 and 4. We now know how to get to E. That's in our spanning tree. E has no new information to give us. So then we'll go ahead and mark G in the spanning tree when we go ahead and take this edge over here. An edge we discovered a long, long time ago and finally decided to keep in the tree. All right, so we've got that. And if we go ahead and just erase the edges that we didn't want to keep, we have that, including the arrows that brought us there. And then we can go ahead and represent. So we killed 1, 2, 3, 4 edges. Killed that, and we killed that. All right, our same spanning tree over here that I guess I didn't redraw, but same spanning tree, right? We had the loop around and then back over. Looped around from E and then back down over across that from F to G. How are we doing with Prim? Not sure I have a strong preference. I think it's easier on pencil and paper to do Prim because you just grab someone and just start drawing out the tree, knocking off, crossing out edges as you come across them. Because yeah, sorting is kind of a pain in the butt. The other thing we have with Kruskal is cycle detection. Cycle detection tends to be fairly expensive. And the way Prim has approached the algorithm, we don't have to look for cycles. We know by the very nature of the algorithm that we're not going to create a cycle because we're adding a vertex to the graph that's not already in the graph. Since it's not already in the graph, it's not possible for that addition to create a cycle. Right? And then all we have to do once we've added that vertex to the graph is just process its edges and update our table. So I don't know what the difference in the time complexities are, but sorting edges would be E log E, assuming a good sort, and a sort that actually is log E, as we've seen many sorts pretend to be log E on average time for the second part, but tend to be actually quadratic. Okay, because all that fun stuff that would be in the links. Grab, oh, I forgot to put the link in here. Let me go get that link back. Prim, there you are. All right, time complexity. I scrolled past it really fast earlier. And you can see the complexity is actually relative to underlying data structure. And we got V squared here versus here we have E plus V log V. All right, so depending on the connectivity of the graph, it looks like they might be using a binary heap. Right, I'm using a table to represent the data that we're tracking, but once we mark something as true, its usefulness in being kept around is kind of not so useful. So it looks like depending on the secondary algorithm used to track the table is driving to the O notation. Don't squeeze your brains too much on the O notations of these algorithms because I don't know what they are. The only one that I know off the top of my head is Floyd-Warshall because it's V cubed. That one, the algorithm, the code and the algorithm for Floyd-Warshall is very straightforward. There's no greedy aspect to worry about. There's not a whole lot of data state to keep track of. It's all in the matrix. You just clone the matrix and then apply the algorithm to that matrix, and the new matrix has the data. With Dijkstra single point shortest path, with our minimum spanning trees, there's way more complexity that that's something if you need the complexity, you can look it up type thing in the real world situation. Because that real world situation, you're going to need to know what the data is. Are we edge heavy or are we not edge heavy? Are we vertex heavy or not vertex heavy? Because that's going to help drive which is the best way to implement the data. Let's get that link there. Okay, let's see. All right, let's go ahead and take another 5-minute break. Let that settle. And then we can continue on. Any questions based on what we've seen so far? All right, let's get to the practice test. See if we have. All right, building our tree. Okay, let's see. All right, so we start with 27, add in 49. 19 comes along. And we can look at a binary search tree at this point. 24 gets added. And we've got 39. Drops over there. 71 causes us to split that node. 49 moves up. Left us with 39. What was it again? 71. And we have the 1924 here still. Now 88. And 45. And there's our tree. So who's in the root? 27 and 49. Questions on number 1 before I blow that away? All right, there's several ways I could ask this question. I could say, what are the two values in the root? What are the two values in the second child of the root, right? So it'd be 39, 45, first child, last child. And second child could, there may not be a third child, so the second child would be the second child still. All right, number 2, build our AVL tree. 35 balanced, 35, 49 balanced, 22 still balanced, 27 still balanced, 64 we're still balanced, and then 41. All right, so no rotations. That should be none of these. All right, if we were to add, say, another value here, 29. Okay, let's try that again. Click. All right, if we were to add 29 here, then this would become alpha. This would have been beta, and we would have been rotating up, in which case the answer to the question would have been 22. Questions about number 2? Ready, steady, carry on. All right, build a binary search tree. Who's on the 3rd level? This one, we know it's not going to be 48 because it's the root and that's not going to change. 55, we eliminate that because that's not the 3rd level. 42, it's not going to be 42, 3rd level, and then we got 37. So that's in our data set, 69, 19, 31, 88, and 53. And so we've got 37, 53, and 69 in our binary search tree. I'll assume no questions on that one. Perform a delete on that heap. All right, scatter heap. So what do we have here? We have 4, 5, 7, 9, 6, 7, 8. Right, so our delete is going to make a hole at the root. 8's gonna fall off. So we need to go ahead and all right. Use this as a candidate. So 5 moves up. 5 moves up, creates a hole. 6 moves up. 8 finds its way over here. All right, so our resulting tree is 5, 6, 7, 9, 8, 7. 5, 6, 7, 9, 8, 7. Everyone recall how I went back and forth from the drawing to the underlying array? Remember, level by level. Okay. First level, second level, third level. Left to right, left to right. Good to go. Yep, binary. Now that's the key with the binary tree. Each level is twice as big as its parent, which is what's getting us, allowing us to cut in half every time we go down a level in the tree. All right, circling down to number 5. Build a max heap. Okay, 17, 17, 12. 24 is going to come along and push that aside. 28 is going to come along. 17 stays where it was. Pushing down, pushing down. 23. 21. 5. 20. 18. 22. And 6. There's my eraser. What are values in the fourth level? Fourth level. So first, second, third, fourth, those small numbers. 12, 18, 22, and 6. Right, not necessarily going to be the 5 smallest. Or the top, remember, if I asked for what are the values in the top 2 levels, it's not necessarily going to be the largest 3. For sure, the largest will be at the root. A second largest might be in there, might not be in there. Yes, the second, let's see. Yeah, the third largest may or may not be there. Second largest will surely be there, but third largest, as we have here, is 23, and that's not in the top. It's way down over here. In fact, the fourth largest is all the way down in this part of the tree. Right? It's not long before it would be deleted out if we start deleting, but because there's no left, right, just up, down, and each branch grows in its own accord based on the data. You need to actually build it. And the only shortcut is, if I ask you a question, build a max heap, what's the largest value in the tree? What's the value in the root? Well, that's the largest value, because that's what the max heap does. All right, in order traversal. So let's draw it out so it's easier to see. 3169, blank, 41, blank, and 75. All right, in order, so we have left tree, so we got the third. Looks like that's a binary search tree, so it's just gonna be in order. 44, 69, 75. What position is the root in the output? All right, so Third position, 3. Let's see if I goofed anything up. Seems I didn't goof on that part. Right, then we have, of course, the fun big O notation of things. Code, any lab code, or whether it was turned in or not, is stuff that can be found on the test next week, which we'll do at the beginning of class, unless there's a strong opinion otherwise. Do it later in the class. Any questions about the test? Test 3. Tests in general. The square root of -1. If you use your imagination, you can. Those good old imaginary numbers. Yeah, math took an interesting turn when I eventually got to that one. my rational and logical brain was like, no, you can't do this. It's impossible. But they're like, well, you can do the cube root of it. So, hey. All right, let's see. Horizon, the hash table did not have the right date. That has been fixed to be the 20th. Can you use imaginary algorithms? Sure, if you're doing mathematical algorithms, right? Imaginary numbers have a very narrow application space. But if you're programming if you're writing the code for a scientific calculator, right, imaginary numbers may well be something it supports. All right, so the hash table, that's hashing. That shouldn't have been up here in the graphs area. I don't know how that date got so messed up. But it did, so it's been fixed. It's now on the 20th because we haven't talked about hashing yet. A couple of you have read ahead, already knew, so you've done it. It's all good. All right, so we have a test next week. Take the test, go over the test later tonight. Talk about traveling sales person, algorithm for complete trees. And probably have time to get into our searches. Not complete trees, complete graphs, search algorithms. There's a breadth for search and depth for search, which are ways that you could do cycle detection that we'll talk about. Might have time for that Monday, otherwise we'll do the 11th. And then should be done with graphs no later than the 11th, and then moving on to hashing from there. I have program 3 to grade, program 4, which is due well towards the end, is based on hashing, so we're not going to talk about that one just yet. I need to create a breadth for search and depth for search exercise. Toss that up there so you guys check that out. Otherwise, 30 minutes, 9:20. Yeah, the rest of the time is just for tonight is just for lab time. So we're still working on program 3, stuck on that. You want me to check out the code? Just ping it to me in Discord and we go check it out, see what's going wrong. And square that up. So we're still missing about a dozen and a half people submitting. So let me know if that's the case. Just toss it in Discord. Otherwise, there's no more lecture for tonight. So unless there are other questions, we can go ahead and stop the recording.